from your favorite artist electronist here. Let's start. I closed all the lights just to have a good contrast here, to see those LEDs there and that one, the yellow one, and also the motor that is running here as well. I will start with showing you the voltage, 5 volts at around 500 but highly fluctuating milliamps. So I have a list of stuff to tell about. This is the final circuit, the final board for this entire project. I am extremely happy that I managed to build it, and it's running as expected, running as designed. First of all, I'm putting my fingers on the transistors here, and they are running longer, like 5 minutes or 10 minutes even, from when I started everything. I've kind of that guy is starting to make some noise now. Not that hard, not that hard. Yes, this is my variable sound. See? It's a toothpick. Okay, so I have a couple of things to discuss about it. Pretty much what I discussed so far, but also my conclusions, because this is, after all, my project, and it deserves a conclusion. And I'm really, like I said, I'm really happy with the output, with the final product. All that it needs right now is a case for protections, for protection, because there are a lot of wires, very thin wires. Let me point it like this. You see this longer wire here, and also a lot of longer wires as well here. This guy, and a couple more that is not very safe at this stage. Especially after a while, after I will, especially after a while, after I will forget about it, and I will not be careful like I am right now. So, first of all, it is made fully, this circuit is made fully of NPN transistors, BJT NPN transistors. These are not, usually you use, in this top side here, you use PNP transistors, and lower side the NPNs, but I used all of them as NPNs, BJT NPNs. Good. Then in the testing times, when I was testing on the breadboard, I got overheating LM317 voltage regulator. This guy here, this guy was overheating for certain voltages. Probably, I don't remember exactly right now because it passed some time from back then. I did a ton of experimentation, so I believe over 10 volts. It was overheating, like 15 volts, 20 volts or something like that. I was driving everything a bit too extreme until I figured out. Actually, I learned a lot by building this experimentation, by building this circuit and experimenting with it and pushing to the maximum everything. And I'm highly recommending everyone to build such a relatively complicated circuit. It's not that complicated, but it is a little bit. You have to pay attention to a lot of details. So that was a problem. But now, knowing the limits, is running cold. Everything actually is running extremely cold, which is extremely good, because overheating means stressing the components, means dying the components in a short time. But running cold like it is running right now is practically immortal, you know, from a circuit point of view. So it will never die. Possibly running all the time like this, forever, because it's running cold. That's the trick. So that's another point on my list here. Another bad thing about it is not driving at the full power of the motor. The motor is not really spinning, and the torque, yeah, he is actually running. He's spinning if I'm trying to catch it, but he is powerful enough. But it's not really pushing the motor to its limits, to its maximum limits, or better say, to its maximum rendement that it can give. This circuit is not built in that direction. It will overheat. And still not driving it. Even if I'm increasing the voltage to 10 volts or 15 volts, it will still not drive or let the motor get the full power, power that it needs to run at its maximum or near its maximum rendement. You know, power like it was designed to its maximum characteristics, just to not to push it, but to actually use all the juice. To squeeze all the juice from it and run it at its best performance possible. So this circuit that I have here, it will not do that, because and I want to add that this is excellent for testing the motors, especially the 4 wires motors, and possibly the 5 wires, but specifically only for 4 wires motors. This is excellent. Because now I will give the explanation. My belief, it's the entire circuit here, the characteristics of every component that I have here. Somehow I cannot explain it with my knowledge that I have. Some other people probably can, but I personally cannot explain it. But my observations, my testings that I did so far, I spend a lot of time actually designing it, thinking about it, testing it, push it to the limits, everything. I spend a good amount of time, a respectable amount of time. And my conclusion after all this time is that having an internal the entire circuit, all these components, all this arrangement that you see here, also here, is having an internal resistance, limiting the motor power and speed. That's my conclusion after all of this. Something here is obstructing or opposing letting full power to the motor, but still is running it. So if I'm increasing, in other words, another way of saying, if I'm increasing the voltage and the amperage from my power supply there, a lot of power will dissipate as heat on the voltage regulator. Very important, this little guy here, this little module actually, and also on the transistors. But these are powerful transistors right now, but still they will eat that power and not let it go to the motor. That's the downside of this entire. This is the most important downside. It will not run at the fullest power, the motor. I stressed it enough, and now you know it very well. These are the bad things, but there are some very good things about this circuit that I designed here. I bet you cannot see this diagram very well, unfortunately, at this distance. I will show it most probably in my screen capture. I will make a screen capture and I will present it probably a little bit more in detail to see it actually how it's looking. I have it, but my printer, yeah, it's bullshit printer that I have, but it's good enough. So this board that I designed here is user friendly. It has variable speed. Let me close this guy here. Hopefully you can see those LEDs there. If I put some shadows there, so also you can see the motor running there. So one of the very good characteristics that it has is this very variable speed. Of course, too much speed is overwhelming. The motor doesn't know how to react to that frequency. Is over its limits, pretty much the speed of the driver here, which is a good thing because you can actually test what is its frequency. If you measure that thing there, yeah, you can with an oscilloscope. Of course, you can measure its frequency and you can deduce its maximum frequency that he can run. So variable speed, okay. All right. Multiple wire combinations. So these are the wire combinations. Let me actually turn on the lights and present it, come on, like this. And I've added some annotations here and there. This is the voltage regulator, 4 volts to 10 volts maximum. These are the limitations. And the nominal is at 5 volts. I've also written on everything there what it means. 555 frequency generator, this module here. That guy's counter here. This is creating the counting actually of those LEDs. This is a NOT gate. It's from here, from this circuit. This guy, and that guy. And these are powerful MOSFETs. Motor coil 2, this sector here. This sector here is motor coil 2. Motor coil 1 is this sector here. And the name of the board is 4-wire stepper motor driver. And I enumerated the outputs, 1, 2, 3, 4. And unfortunately, I didn't add the color wires. I should have, but yeah, well. And these are running exactly as I plug it in as 1, 2, 3, 4. These wires of the motors. But the other motor that I have here is having a little bit different wiring, and that's what I wanted to show you. So I said is multiple motor wire combinations. This is what I mean by that. So this is my noisy motor here. That is. Let me add this noise suppression variation toothpicks, and let's put it like this. And right now it will vibrate because the wiring is not correct. All right, can you see it like that? And that's the beauty of this design. I actually put the numbers there. 1. Let me take them out from here. 1 on 1, 4. So this wire here will go to 4 here, and this wire here, its third wire will go to number 2 here, and the last one to number 3. Yeah. Oh yeah. So that's the order. And right now it's working. So so multiple motor wire combination. And now if I'm plugging this one here, this wire combination will not work for both of them, only for one. And this will tremble as well, like an idiot. It will not know what to do. It's not, but it's very good for testing the wires. That's the idea. One of the idea of this circuit. I really liked it because of very simple wire combinations, and it's good to find the wire combinations for the 4-wire motors. Unfortunately, I'm not sure if it will do a good job for 5 wires. I will have to test it later in time. So let me put this guy back, and of course we can change the sense. Let me actually stop it and do like this. And if I want to turn the other sense, I'm turning the plug here. So now it's going clockwise, right, like that. This is counterclockwise. It's going like that. So that's good. That's very good way of testing the motor wires, to figure out the motor wires. Of course, it's overcomplicated circuit only to test the wires, but it's a fast way. It's a fast way of doing it. After you build it, of course, you first must to build such kind of circuits. You know, you have to have the pleasure of making them, and they will become very useful in the long run. You know, hopefully. The next thing on my list here is two speeds, ×1 and ×10, which I have already presented them already. I have these two speeds here. I will quickly go over them. Right now it's on ×10. As you can see, it's cycling. Let me close the lights for those LEDs to be seen correctly. Now, if I'm switching to ×1, look how slowly it is running and waiting, and then starting to count. Actually, this circuit is not that good, but I leave it as it is, because the 4017 counter integrated circuit that I have here, this guy that I'm pointing with my knife, is having some pins broken, and I still make it work with skipping the previous pins that was broken and continuing on the pins that were good, pretty much. So he is counting from 0, 1, 2, and then or 0, 1, and then starting from 2, 3, 4, 5, 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5, 7, 6, whatever. So that's the idea, that is keeping some pins, but using the rest that were good pins. So it's having a little bit of delay, but it's okay. And this guy is actually working, as you can see, and you see, per each step. That is doing very extremely slowly, because we are talking about this X1 and X10. So right now, if I'm putting it to its maximum speed, the motor cannot run at maximum. But if I'm switching, but you can see the flashing of the LEDs there. You can see how fast, and you can see the flicker of them. But if I'm switching to X10, you will not see any flicker. They will just be like continuously lit. So let's do that, you see? And the motor, you can hear it. Yeah, so I'm turning it way back to actually make it running. So this is a very neat option, and this is the maximum. This is the minimum for X10. Remember, on X1 was very slow, but this is quite fast for the minimum. And what I used here, I used two capacitors, this guy and this guy. I hope you can see them. And I've discussed already this subject. I explained it in my preview video, and you can watch that if you want a better explanation of this circuit here. By the way, it's using a 555 integrated circuit there. And this yellow LED that you can see here is just a power LED, just to tell me that the entire board is powered. If I'm having some problems, if those LEDs were not lighting here, that power LED will tell me there is coming 5 volts through the voltage regulator here. It's after the voltage regulator. So yeah, pretty much. So I have, this is another good thing, I have two speeds. Yeah, it's a very safe circuit, both for the motors and for itself. It's not overheating. I am respecting this voltage limit from 4 volts to 10 volts, maximum 10 volts, and working nominally at 5 volts. Usually all the tests that I did so far, I did them for 5 volts. And it's extremely safe from this point of view. Nothing will burn out, nothing is overheating. It's very optimized. Like I said, like I already said, running cold. Everything is running cold. Running from 4 volts to 10 volts safely and not overheating. I already covered that. Over 10 to 15 volts will overheat, but I don't really, it can go there to 15 volts, it can go, but it's a bit risky and I rather not do it. If something there will heat up and die, it's really hard to change it. That's the problem. So I would rather keep it safe, in the safe zone. I'm using very powerful transistors because I have another transistors that I put my eyes on, and they are actually coming. I made a purchase. I've already buy them. They are coming in the mail, and they are way more powerful than these guys that I have right now. But these are they are powerful, good power they have. So my upgradable version of these powerful transistors that I have here, these are called BD 441s here, and here on the bottom they are BD which one? 139. Actually, I have the data here. BD 139 for the lower side. So all these guys here are the 1.5 amps at 80 volts, 1.5 amps, 12.5 watts. So medium power transistors. While the BD441s that I have already right here are 80 volts, 4 amps, 36 watts. And the next one that I put my eyes on is what are you? BD681 at 100 volts, 4 amps, and 40 watts. A little bit higher in wattage than these guys here. Not much difference, but it is a difference. And they are and cheap enough, you know, very cheap. Not very cheap, but cheap enough. But I took a lot of them. That's the idea. Okay. This circuit also is overprotected, meaning that I put here, I'm not sure if you can see it clearly. Probably I will have to explain it in my diagram on a screen capture. But here I have the 4 diodes that are protecting for overcurrents, possibly overcurrents that I had in my testing. I had some burned circuits, integrated circuits, and I put this diodes here for for protection. And these guys here as well for these guys are rectifying bridges, this and this, and they are this round components here. They are back EMF protection diodes, pretty much, and they are protecting the transistors, all the transistors here. Well, this guy is protecting all these four, and this guy is protecting this other four from the electromagnetic force from the coils of the motor that are pushing spikes, pretty much. They are anti-spikes, over voltage spikes that will burn out the transistor. These transistors are for 80 volts, but probably the spikes will go to a couple of 100 volts, and they will fuck up the junction of the transistor. So those diodes will not permit that spike to happen, pretty much. Right. The next board that I will build after this board, probably it should be. I've already coincidentally yesterday I received this L298 dual H-bridge driver chip for 4-wire stepper motors. I put there. I mentioned that. I like to put my sticker to be very specific and to read it and remember what everything is. It's very good advice, and I really like the case. Very nice from AliExpress, not from eBay. Yeah. And the next board will be with these guys. I'm actually planning. I have I forget how many motors I have. These brand new guys. I have 5. I think 5 of them. Yeah, 5 of these guys here, and also some scrap motors. This one and a few others, not many, with 4 wires. I don't have that many with 4 wires from the scrap. But these are brand new, and I want to make. The plan is to make a driver for each of it, and hopefully this is my hope, this is my desire, my target, to fully drive the motor at its maximum potential, maximum rendement, pretty much, and not 50-50 like it is right now. So that's with L298, this guy here, but also with MOSFETs. So that's the next boards after this guy. And the last point that I should have mentioned before, I looked on in my discussions on AAC forums that I'm usually there all the time, and I'm highly recommending that forum for electronics and even programming, for microchip microcontrollers and other types of microcontrollers. Probably they are very knowledgeable guys. They're very helpful, and if you behave, you can get very easily friend with them, and they will help you. And after discussion, a lot of discussion about many aspects of this board that I'm doing right now, they showed me some links. I searched also a lot of other boards for driving motors, and I noticed that every driver, every stepper motor driver, and even DC motor drivers, they are all using heatsinks on the transistors. And depends on the board, but if I remember right, I've seen a heatsink also on the power voltage regulator here. But usually you will see heatsink on each transistor or on each chip, integrated circuit they use. Even on this what is called? How is it called? L298 chip, they have a heatsink, a dedicated heatsink, aluminum heatsink like this guy here. And the only problem that I have, I don't have this kind of heatsink for this guy, so I will have to figure out something from the scraps that I have, or actually buy a dedicated heatsink for these guys. I will see in time how it will behave and how hot it will run. But if it will be calibrated correctly to run it, not overrun anything, just run it at optimal power, probably it will not overheat, or not too much, And this is the thing with heatsinks. It's a must component. You have to think about it, about this heatsink. This is a lesson for me from building this circuit. Not the only lesson, but one of the lessons that I learned, and I think is an important one to tell you, that heatsinks are. You have to think on heatsinks as a component, to include them like you are including a transistor or a resistor. You have to think in those parameters as a power dissipating, heat dissipating device, if you want. It's not a device, but you must think like that, in that direction, like it is a device that you attach it to the component that is overheating and is doing some good, is taking the heat from it and dissipating it and helping the component a little bit more than if it wasn't there. If you observed also on processors, they are actually use heatsinks on processors, like the CPU on a motherboard on your computer. They are always use heatsinks there. I never seen a CPU on a motherboard without a heatsink. I don't remember seeing one in my life. Or if I've seen one, I completely forget it. But probably those were the first computers in the very beginning era of computers. But the modern CPUs until now, they were using heatsinks as a valuable component, pretty much, and that's important. Yeah. And pretty much this is it about everything. I think I covered almost everything important about this board, and hopefully you like it, and you will build it as well, and give me some thanks and likes. I'm not really hunting from any kind of likes, but yeah, if it's helping anybody else there, it's a good learning circuit, and you will learn about power, power transistors, power dissipation if you want, and heat dissipation if you want, and motors. Yeah, thank you very much for watching. Thank you very much for listening, and I will leave you from here, from Romania, from your favorite artist electronist here, and Q12, and see you later, alligator, as I'm always saying. Thank you very much. Bye bye.